All right, everybody all fresh and ready to go at 9 a.m.? Shirley and I both noticed a difference in the energies of our audiences, whether we were lecturing at 9 a.m. or a little bit later. Thank you for being here. Today, I want to get to inferring the Hubble constant from CMB temperature data. Not that we're particularly interested in exactly how fast the universe is expanding today, but there's an interesting discrepancy with more direct ways of inferring the expansion rate today that may be an important clue. It's not clear. I've spent a lot of time thinking about this and how one can change cosmological models to possibly explain this. Then I'm going to talk about, so this is just from, in the LambdaCDM model, using the physics that we've been working up to with the CMB temperature power spectrum yesterday that will continue today, constraining light relic abundances from CMB temperature anisotropy maps, and this parameter called NF. And then I'm going to talk about something that we call this FFAT scaling or FAT scaling, which is a transformation on some theoretical quantities that keeps a set of interesting observables unchanged. And this was a thing we noticed in the equations of motion that we then exploited to pose a solution to this Hubble constant problem that implementing it required, well, our way of implementing it was to include something called a mirror world dark sector. So I'm hoping we can get to that, and my eagerness to get there has led me to put up this stuff on the board ahead of time. Let me give a recap. Of course, if we don't get there, we don't get there, and I don't want you all. So please do interrupt and ask questions. Recap of lecture 2. So I talked about superhorizon evolution, where in the LambdaCDM model, in the radiation-dominated universe, all the modes that we're observing today, all the wavelengths of perturbations that we're observing today, spent this time outside the horizon, where all the peculiar velocities of the plasma damped away. So when they began to oscillate, they all oscillated with the same phase, and so modes of a given wavelength oscillating at the same frequency all are in phase together. And this leads to these peaks in the CMB power spectrum from these standing waves. Right? You have these standing waves oscillating in a temporally coherent manner. And this leads to these peaks. And we talked about how you can use this peak spacing to infer the angular size of the sound horizon. This is known to, I think, better than 0.1%. And what is it? It's the angular size of the sound horizon in projection today. We're going to see how that's used in inferring the Hubble constant. Then we talked about gravitational potential decay at horizon crossing. So as modes enter the horizon, if there's significant radiation present, then the matter, including the radiation, won't collapse into potential wells fast enough to sustain the gravitational potentials. They decay, and so you have gravity driving the fluid into an overdensity, and then just as it's about to bounce back, fighting against gravity to come out, gravity has disappeared, so that it resonantly enhances the amplitude of the acoustic oscillation, and the amount of that effect, and it's a dramatic effect, depends on this. So this gives us great sensitivity, in the LambdaCDM model to this ratio. And in the LambdaCDM model, we know the radiation density. It's not a free parameter. And so we can infer the matter density. More generally, anything that's influencing gravitational potential decay has an impact. So that's recap of really everything from lecture 2. I just barely got started talking about photon diffusion. And So photon diffusion happens because this epoch in which we transition from an ionized plasma, ionized and opaque plasma, to a neutral gas, right, where the mean free path of a photon is basically 0 in this, because of the high number density of free electrons, to where say the mean free path is comparable to the horizon. This is not instantaneous, right? This happens over some time, and while that's happening, photons are diffusing from their original location. So I've just drawn a plane wave here of modulations of hot, cold, and imagine that you're looking, you're looking out at the sky, and in projection there may be, let's look at what happens with a given photon here. It starts off in this hot region. Initially, the free electron density is very high, and so it's readily scattering and not getting anywhere. Then the free electron density drops and it starts moving, and then maybe this is where it is when it last scatters. So let's say this, this is a photon that then comes toward us. Same thing, of course, happens with photons in a slightly colder region. And so there's some typical distance over which a photon diffuses via this random walk that we call, or at least the notation I'm going to use today, is this R sub d, d for diffusion. So that's the typical co-moving distance a photon travels before last scattering. And if we define kd equals pi over this diffusion distance, then modes get damped approximately by e to the minus k squared over kd squared. And this is a result that's, you can expand, you can do a perturbative expansion in the ratio of the mean free path to the wavelength of the perturbation. That's called a tight coupling expansion, right? How big is the perturbation wavelength compared to the mean free path? You can expand in that quantity. To second order, in that expansion, you get this result that there's this damping. Now, we're applying this tight coupling to get this, we're applying this tight coupling approximation just as the mean free path is becoming very large, right? So this is a dicey thing to do. This gives you a rough guide to the damping of the fluctuations. Now, how do we calculate this diffusion scale, or at least get a rough idea of what it is? Let's see, maybe I'll leave this here and go over here. So a rough calculation, just to give you some physical intuition for it. And that's the co-moving length, so let's think about the physical diffusion length. So this is going to be, because it's a random walk process, this typical distance is going to go as the square root of the number of steps taken, and then times the length of a step. Of course, right, the step length is varying through this process, but let's not worry about that right now. This is just to get us a very rough idea of what would come into the diffusion length. So what is let's see, the number of steps is approximately, well, the age of the universe up to the point of time we're talking about. The distance a photon would travel in that time, which is, anyway, just roughly it's this, divided by the mean free path. so this it's roughly this. Shouldn't put an equal sign here. Right? There's factors of order unity relating 1 over h to the age of the universe. And and that mean free path of a photon surrounded by these, traveling through this these free electrons is just given by this. And so what we get here is h sigma t n e to the minus 1/2. So for our purposes right now, the thing to note is this depends on the free electron density. And so this effect, this effect depends on the baryon density. And we can use measurements of this damping, measurements of the shape of the power spectrum below the, as we go further into this modes that are damped by this diffusion, we can use that to infer the baryon density. If we know the atomic physics to relate the baryons to the electron density at any given time, then we can infer the baryon density, which we also often write as this. You may have heard of other ways to infer the baryon density from the temperature power spectrum, but this is an additional way, and the one I'm covering right now. Anyway, before I go on from photon diffusion, any questions about the process or about what I wrote down? I mean, this is it wouldn't take too much longer to actually derive a much more accurate expression for this that would be an integral over time and treating this properly. But just to give it's a random walk process, so it shouldn't be surprising that you have this 1 over the square root of h in it. That's giving you that's like going like the square root of time, and then and the mean free path is entering into it. Yeah.
So it depends on the electron number density.
Mm-hmm.
So how can you directly infer the baryon density from it?
So we have charge neutrality. Oh yeah. So the question was, how do we translate electron number density to baryon density? Right. That's your question, right? And so the number density of free electrons is actually, let's see, if we just have a hydrogen-only universe, which is not too, actually 94% of the nuclei are hydrogen, so this isn't so far off reality. Hydrogen-only universe, then the number density of electrons equals the number density of protons, and this equals, I guess, the some ionization fraction times, say, number density of free protons plus number density of hydrogen, right? So this is the ionization fraction. This is what you need to do the atomic physics to calculate. So you know the atomic reaction rates, right, in the history, and then this is, of course, the baryon density. So, and now actually, if we include helium, so if you include helium at fixed baryon density, what the helium does, so to make helium out of hydrogen, you need to suck in electrons, and then also the helium at the point that's important here is actually neutral. These are neutral helium atoms. So they suck up a lot of electrons, adding in helium. And if you include helium, then Ne equals Xe Nb times 1 minus Yp, where this is the fraction of baryonic mass in helium. So, but in LambdaCDM, helium is not a free parameter. We calculate this using BBN, and we can calculate the ionization history. So we can infer the baryon density. Thank you for that question. Yeah?
The final equality you wrote there, that's ARD and not n steps, correct?
That's what?
Is the final expression there the H sigma T and E minus 1/2?
Yeah.
That's A times RD and not n steps.
Oh, thank you. Yes. Yeah.
Maybe you already said, but when is this time that we calculate this number density of this?
Oh, right. So this is, so if I were the important time here is a time of recombination. And actually, if we were really going into the subtleties of this, that's an excellent question. Because, I mean, as I just said, if we draw something called so this is redshift, and this is like 1100, there's this quantity we can calculate called the visibility function, looks something like this. And so this is, z equals 7. And this is the probability for a photon that we see today. Where did it last scatter? dp dz, right? The probability density. And so we're seeing photons from over this thickness, this range of thickness. And so as we're sampling this, we're really sampling different amounts of diffusion. So to the extent we're seeing photons from this redshift, right, and we are seeing some from then, there's less amount of diffusion. And then we're also seeing photons from here where there's more diffusion. So we're kind of getting this mix of maps that have different amounts of diffusion in them. But this is the time that matters. Thanks for that question. OK, so let's look at how now we can get the Hubble constant from CMB in LambdaCDM. And the reason to focus on this is that if we look at our R, meaning the community's most precise measurement of that is not cosmology model dependent of the expansion rate, it's 5 sigma discrepant from what you get given assuming LambdaCDM and using CMB data, using Planck data. And you get consistent results from other CMB data sets. You can get consistent results assuming LambdaCDM and not even any CMB data. So I mean, it's an interesting situation that possibly is telling us something about cosmology, possibly about the dark universe. It's not clear yet. So let's look at how you even infer H naught assuming LambdaCDM. So we have omega matter already. This is density of matter from this radiation driving effect. We have the baryon density from diffusion damping. And we have the angular size of the sound horizon from the peak spacing. We also know the radiation density, right? We just, because it's specified in the model, we know the whole history of the photon energy density and the neutrino energy density. So we have the matter, except for the cosmological constant, we have the matter content that's important pinned down, or at least determined with some small errors. And there's an important quantity we can calculate just from these two things, which is the sound horizon at recombination. So this depends on just the baryon density and the matter density. And the reason is that up to recombination, which happens just a factor of 3 in expansion after matter radiation equality, when the cosmological constant is definitely not important. Knowing the matter density, which is cold dark matter plus baryon density, knowing that, you know that, and the radiation density, you can calculate the history of the expansion rate. So you know the history of the expansion rate. You know how the universe has cooled from infinite temperature down to atomic physics temperatures where recombination happens. And then the baryon density controls the sound speed. The baryon density is telling us the baryon to photon ratio. The more baryons you have in the plasma, the slower the sound speed is. So you can calculate the sound speed with this. So you know the sound speed, you know the history of the expansion. You can calculate how far a sound wave will travel from the beginning until decoupling. And then we can do the atomic physics to know, when this decoupling happens. It's hard. It's out of equilibrium. It's significantly out of equilibrium. So the ionization history, if you had chemical equilibrium between electrons, protons, and hydrogen atoms, the ionization history, ionization fraction would change really rapidly. And so rapidly that the atomic reaction rates can't keep up. So this is an out of equilibrium process. It's a significant technical challenge to calculate it, but people have done it, and it's doable. Yeah.
Yeah, I remember when we calculate the fluctuations, we assume that parts are very small in comparison with the dark matter. So, and what you're saying that the speed of sound is dependent on the baryon density instead of the dark matter.
Because the dark matter is not interacting with the photons. They're not part of the plasma. The question was, I'm talking about the speed of sound influenced by the baryons. But there's a lot more dark matter than baryons. So why am I not talking about the dark matter? And the reason is because this is the baryon, the fluid of baryons, electrons, photons is not interacting with the dark matter. So it's not changing the pressure, right? So it's not influencing the sound speed. Yeah.
I think I have the opposite question. Why is WM in there if it should only respond to the density of baryons and maybe radiation?
It's in here because how fast you expand affects this, right? So if you expand really rapidly, which you would if you had a higher matter density, if you expand really rapidly, then the sound horizon is going to be smaller because it took less time to cool down. Yeah.
Are we assuming anything about the curvature of the universe to keep balance of the mass energy density?
Absolutely. So, but at these times, so let me write down the Friedmann equation. And this is scaling like, so this is the curvature contribution to the expansion rate, and this is scaling like 1 over a squared. Even today, it seems like this. We have tight bounds on the curvature, and even if we take those bounds at 10 sigma, maybe we got something wrong. At these earlier times, this is really negligible, right? We've got rho matter going like a to the minus 3, rho radiation going like a to the minus 4. So when the scale factor is 1,100 times smaller and even smaller than that, this just isn't important. So yeah, and back. Okay. And this leads to this weird thing, right? Physically, it seems weird. Wait, how come I add in more energy density that's kind of gravitating and trying to hold things together, and I get a faster expansion rate? It's because of this term here. It's because of this assumption that this is 0. So that if you add in more energy density and you want k to be 0, you need to increase the expansion rate. Right? But if you just took a universe and then somehow added more energy density into it, and kept the expansion rate the same, then you'd have this curvature term up here. Yeah. So was that actually the origin of your, maybe, okay.
Yeah, I was wondering if it's measured k equal to 0 or
Yeah.
it's an assumption.
Yeah. I mean, this does present us with a standard ruler. Well, anyway, I'm getting ahead of myself. I mean, we do use this to investigate the geometry, but in the next step, we're definitely going to be assuming the k equals 0. Okay. So theta s equals rs star over dA star, and right. So we have this here. And so we have RS star. We've calculated this. We were measuring this essentially from the peak spacing. And so we can infer this. Right, measured, calculated. Observed. And so what does this depend on? So this distance to last scattering to 0, let me write 0 to z star, works out to a particularly simple expression here. I mean, intuitively, right? The more rapidly you're expanding, you would expect a shorter distance between us and last scattering. What defines, what really sets the last scattering relative to us? We know that the universe has expanded by a factor of about 1100 because the temperature of the CMB is about 3 Kelvin today. And we know that this decoupling happened when the temperature was around 3000 Kelvin. So if you expand really rapidly, then a photon won't travel much distance between then and now. So we get this inverse to the expansion rate. And this depends on, right, the history of the matter content through the Friedmann equation. We know everything. We know the whole matter content except omega lambda, right? So it depends on this. There certainly depends on the density of the cosmological constant. We're evolving it to today, right? And so that'll be contributing to the expansion rate. So the only unknown quantity contributing to this is the cosmological constant. So we can infer the density associated with the cosmological constant. And if we know the density of everything, then we actually know the whole history of the expansion rate. Certainly we know the expansion rate today, the Hubble constant, h0. So that's how we can infer the Hubble constant in the LambdaCDM model from measuring these dimensionless things on the sky, right? Delta t over t of theta comma phi. Okay, so any questions about that before I go on to light relic constraints? Yes?
I actually have a question about this nature. So let's say we live in a different universe where k equals 0 for sure.
Yeah, okay.
So does this mean more matter is increasing?
More matter. Well, we're so now you're comparing two different universes. Is that right?
No, I'm just talking about the new universe where k equals 0, like exactly.
But then you want to make some relative statement.
And then may I ask, is that in that universe, the space is like proportional to the matter, the density of matter?
Right. There's another way to think about this expression, and let me write it as h squared minus 8 pi g rho over 3 equals minus k, and let me multiply these by a squared. And this is, this term you can think of as kinetic energy. I mean, you can derive this from a Newtonian analysis, and this is kinetic energy. This is gravitational potential energy in a Newtonian picture. And in this Newtonian analysis, this is the total energy. Of course, the Newtonian analysis won't tell you that this is something related to geometry. You need general relativity for that. Is this, I mean, so this is, maybe this will be helpful to you, right? So we're, setting k equals 0 is just this assumption that we're basically have escape velocity, right? It's completely analogous to that. Yeah, and so if you have escape velocity and you increase the mass of the planet, you better increase the velocity of the thing going away from it. So it's the same counterintuitive thing. You increase mass, you get a bigger velocity. It's because you're doing this comparison between models.
What the parameters are going to change if I assume the other value of the Hubble constant?
So the question was, how are the other parameters going to change if you assume a different value of the Hubble constant?
Yeah, I'm talking about the Hubble tension.
Yeah, so we're actually, we'll really go through that with LambdaCDM plus NF. And it depends on what you decide to hold fixed, right? And a reasonable thing to hold fixed is, well, we'll talk about what you should hold fixed while you're trying to adjust to boost the Hubble constant. Okay, so let's see. Maybe I'll just lift this up. So let's think about constraints on light relics. And we'll use this physics that we've already introduced to do this. And let me define, so I said the word light relics, and I wrote down NF, which is probably a parameter you've seen before. And let me say, of course, why this subject is interesting. So this is constraints on NF. So constraints on light relics, thermally produced in the Big Bang, is one of the main contributions of cosmology to model building in particle physics, or one of the main things that model builders have to take into account. Any light stable particle thermally produced in the Big Bang will contribute to the energy density, and later on, and one has to check and make sure that that's consistent with our constraints on that energy density. And we parameterize that with this quantity NF, which is the effective number of neutrino species. And one way of defining NF, which connects directly with that meaning, is that it's the density of what I'll label as X, anything dark and light, anything relativistic and non-interacting with, not interacting much with the standard model, over what is almost the energy density you'd get from a single species of neutrinos. And I'll explain the almost in a minute, but the tilde here is to capture that almost. And the almost is because this is the expected density if all the E plus E minus entropy was dumped into photons and none in neutrinos. this is a pretty good approximation, right? Because the electrons and positrons become non-relativistic and dump all their entropy into the other particles after the neutrino, well, pretty much while the neutrinos have decoupled from the rest of physics, except for gravity. But not quite, and that's why the tilde. And as a result, in LambdaCDM, NF is not 3. Right? In LambdaCDM, the only dark and light relics are the neutrinos. There's 3 species of neutrinos. And if it weren't for some of the entropy going into the neutrinos, this would be 3. But a little bit of that entropy actually makes it into the neutrino background. And so we have this 4-4 here. OK, so that's what NF is. And we're going to look at how we constrain this, how we determine it from CMB temperature data. And actually, in thinking about this, we're going to be following up exactly on his question. What parameters would we adjust to try to accommodate a different value of NF? And so, and let me remind you, one thing we're sensitive to, and it should be right here, we're sensitive to this ratio. So, right, because of this radiation driving effect, this matter to radiation ratio. So if we increase NF, and we want to still have our model be consistent with data, what else should we change? Right, the dark matter density. So we don't, so this effect is how we infer the dark matter density, right? That's how we know it. In the LambdaCDM model, we just know the radiation density, so we can use this to infer the dark matter density. More generally, it's telling us about the ratio between non-relativistic matter and radiation. If we add in more what we count as radiation, that's relativistic particles, then we can increase the matter density, and we're fine from that effect. So if we scale up the radiation density by increasing NF, we're going to want to, we can compensate for that by scaling up the matter density, and in particular by we can't scale up the baryons, so what's being scaled up here is the cold dark matter density. We're doing that by scaling up the cold dark matter density. OK, we also want to preserve the angular size of the sound horizon, right? So that's inferred from these acoustic dynamics. And so, right, that's one thing. So how is this ratio affected by this scaling? So what is the scaling going to do to the expansion rate? Right, so I see some people pointing up. Good, yes. So if we increase the energy density, we're going to be increasing the expansion rate. So so what's going to happen to the sound horizon? I'll take closer to mean smaller. Right. So this right. If you're expanding more rapidly, there's less time for a sound wave to travel. So it's going to travel a shorter distance. The sound horizon will be smaller. And in fact, it'll be smaller by, RS star is I mean, it goes as some integral over 1 over h of z, but you're uniformly changing that, so it's just scaling as this, so proportional to 1 over the square root of the scaling factor. And so RS is going to go down like 1 over the square root of lambda. In order for dA, we'd like dA to do the same thing. Right? dA is just simply given as this integral dz over h of z. So if we scaled up the rest, the only thing we haven't scaled up here, as far as what contributes to the expansion rate, is the cosmological constant. So we scale up the cosmological constant. What was it? Right. Rho lambda goes to lambda rho lambda. Then all the energy densities scaling up, and so the expansion rate's scaling up uniformly everywhere, and so we get dA also, scaling like 1 over the square root of lambda. So that preserves theta s. So we can accommodate additional light relics as far as these two constraints are concerned, just by scaling up energy density everywhere. But what other effects should we be careful about? Yeah. Well, sorry. Yes. Well, it depends on what we decide to hold fixed. And maybe it would have been helpful if I told you about. Anyway, what we're thinking about now is a model space where we have LambdaCDM, and we've just extended it by allowing for additional light relics. So the curvature is still 0. You're onto something, though. So if we force this to be 0, right, that's part of our model assumption, and we increase the energy density, all we got to do is increase the expansion rate, right? So that's what that's why increasing the energy density has led to increasing the expansion rate. Thank you.
Is there a reason to increase radiation in off matter?
So our starting point here is how do we constrain additional light relics? So those contribute to radiation. So that's our starting point. We're interested in constraints on radiation. So radiation, again, I mean anything that's relativistic. And then we are actually in accommodating that. One thing we've done is we're also realizing the best way to accommodate that is actually, or part of accommodating that is increasing the density of cold dark matter. Right? So we actually are increasing matter density in this little thought exercise.
Just to be clear, so when you increase the density, dA gets smaller. Shouldn't RS also get smaller by the same amount, so that theta?
That's the point, exactly. So if we scale up the density everywhere, then RS and D both scale by the same thing, and so the angle's preserved. Right? Yeah, exactly. And that's what we want, right? That's what's related to this observable, which is this, which one way to think about it is that this spacing between the peaks is telling us about theta s. And right, as we do this, none of this has any effect on actual observations. Right, so that's all staying fixed, the observations. Just changes our model of the signals in the observations. Okay, so we've, what other effect in the data should we be careful about, right, that we actually use to do some of this constraining in the LambdaCDM model? Yes? Oh, well, yes. I mean, actually measuring H0 is very relevant. That would be informative. But I'm looking for an effect in the CMB data that we've talked about. So absolutely. I guess I'm inconveniently covering up this board. Right? So there's the photon diffusion effect. We haven't thought about that yet in the context of NF. And this photon diffusion effect has a particular scaling with the expansion rate as well. And so this diffusion scale is going like 1 over h to the 1/2. So it's going like 1 over lambda to the 1/4. Now we see the diffusion in projection, of course. We don't have any sensitivity to this actual. Did any of the other lecturers drop this mic? Is it just me? Thank you. Okay, so we don't actually, see this. We see this all in projection, right? Angles on the sky, and this. So we need to preserve this diffusion angle that we're sensitive to. Projected over the same angular diameter distance, and so this observable quantity is now scaling like lambda to the 1/4. Wait a second. This is right. Lambda. Wait, am I getting this? Yes. So, if we, there's other. At this point, you might say, well, can we adjust the baryon density? Right. And if this were the only effect constraining the baryon density, we could adjust the baryon density and then compensate for this. There's another effect. I mean, the baryon density is changing the pressure of this fluid. So it might not be surprising to hear that there's other constraints we have that I haven't told you about on the baryon density. And just to say it in a word without explaining it, there's this odd even peak height modulation that if you change the baryon density, you modulate, you move odd peak heights up and even peak heights down. We can talk about it during the coffee break if you're interested. So there's another constraint on the baryon density. And given that, and since we're fixing helium, because we're just doing LambdaCDM plus NF, this is fixed, and we're getting this scaling wrong because this minus 1/2, and so we're stuck with this. So in this LambdaCDM plus NF model space, the damping tail is a critical part. What we call, this measuring the CMB anisotropies out past the diffusion scale is an important. This is critically important to the constraints that we get on the density of light relics. And just to quantify that, so from temperature anisotropy alone, get NF equals 3.00. You might be expecting really small errors after this, but I think it's a coincidence. And this is at these are 95% error bounds. And I mean, one thing I want to say about this, so one thing I think is really cool about this is that it actually tells us that, yes, the electrons and positrons dumped their entropy pretty much after the neutrinos decoupled, as expected. And it's amazing, right, that we're probing processes at that early times. Why do I say that? I say that because if that did not happen, let's say E minus, E plus went to shared this entropy with photon. Let's say the neutrinos hadn't decoupled and this entropy was shared, then the value of NF we would have is about 8. Right? So this is, we've really strongly detected what I call electron-positron cooling of the neutrinos. Right? It's cooling the neutrinos relative to the photons. Right? The electrons and positrons heat up the photons. And so as a net result, we expect that the neutrino background today has a temperature of just below 2 degrees Kelvin, right, while the photon temperature is 2.73 degrees Kelvin. And this is totally inconsistent with that entropy being shared with the neutrinos. Now, my next question I had is, so we do have this constraint in this model space. One of the challenging things as an outsider, I think, consuming these constraints is that it's all model dependent, right? I mean, we're looking at fluctuations in the intensity of light on the sky and then concluding these things. You know that a model was crucially important in this. But in this model space, what's happening to the, if we manage to increase NF some, and there's some room to do it, what's happening to the Hubble constant? This has already come up. What do you expect is happening to the Hubble constant as we increase NF? It's going up, right? We increase the energy density everywhere. We increase to best accommodate the data, we've also increased the value of the cosmological constant. So we're going to increase the Hubble constant. Because the Hubble constant presents us with this challenge, it's interesting to ask, is there a model space that can allow us to boost NF up further? I mean, NF is a very well-motivated extension to LambdaCDM, right? All you need to do is something that thermally produces long-lived particles, light long-lived particles in the early universe. So is there something we can change about the model to allow for a higher Hubble constant? And that brings me to this last subject I want to talk about, which, let's see, maybe I'll go over here and erase this. Which is called, which my co-authors and I decided to call fat scaling. And we'll get to why. And it gives us a clue as to a model extension that'll work. To solve the Hubble constant problem. Oh, it does run into some critical issues, and so we have not yet solved the Hubble constant problem. Yes?
When you define n effective in the board, that is, so that row of x, that's the total radiation energy density of the universe, or just the...
This is just the dark and light.
So even if I produce, like, let's say, an ultra scalar from freezing, which is not thermally coupled to thermal, but that would affect n effective.
So the question is about whether some particle produced would contribute to this, and if that particle is still relativistic at recombination, and it's not interacting significantly with baryons or dark matter or photons or neutrinos, then yes, it would be well modeled by how, anyways, by what I'm thinking of as living here. Yes. Yeah. Yes.
So where does this like 3.044 number come from? Like, is this assuming the central values of all the other CDM parameters or something, or is it insensitive to those?
So
Just because
this is
precise, then.
so there's all these things that I talked about on the first day that are assumptions of Lambda CDM. It depends on those, right? So it depends on the thermal history, and it depends on things like that we assume that the lepton number is close to 0, and that there aren't any additional exotic processes going on.
But it doesn't depend on like baryon density or something like this, or.
Let's see. Does it depend on it? No. Remember the baryon to photon. Let's see. It may have some. It must have some small dependence on the baryon density. It may, but yeah. Let me anyway. It's a great question, but I'm gonna. We could discuss it longer, but it's right now. It's as far as where our experimental constraints are now. It's pretty small. And anyway, let me move on, or I'm not going to get through talking about the scaling transformation. And this name, let's see, what do I want to say to motivate it? So what it is a discovery of a scaling transformation that leaves all dimensionless observables invariant. So we were kind of going, we introduced a scaling transformation here, right? We realized, okay, if we scale up all these energy densities by something, then at least some things remain invariant. You can think of this as an extension of that actually does a much better job of leaving the observables invariant. Not just CMB temperature, but CMB polarization, CMB gravitational lensing, delta rho over rho, so baryon acoustic oscillations. Any dimensionless thing in cosmology is basically left invariant by this scaling. So what is it? Well, it actually comes from basically dimensional analysis. So if you look at the Einstein-Boltzmann equations, all the dimensionful coefficients in the problem are rates, can be cast as rates. There's what we call the gravitational freefall rate for each species, square root of g times rho I. So this is the freefall rate for each species, and right as a function of redshift. So this is changing with time. It's not just a number or set of numbers, and then the Thomson rate. From these, one can get the Hubble rate at any epoch. So that's certainly an important rate. But these are the only rates in the problem, and then we're usually thinking about these one wave number at a time. So the wave number itself is a dimensionful coefficient that comes into things. In principle, the atomic reaction rates are important too. I told you that this reionization, this process of recombination, calculating the ionization history, this is out of equilibrium. It's sensitive to the values of atomic reaction rates. But let's ignore that for now, and given our time probably for the remainder of the lecture. Turns out not to be an issue for applying this. So if we consider this transformation, we send any k to lambda k, square root of g rho I to lambda square root of g rho I, and sigma t ne to lambda sigma t ne, then the equations of motion are unchanged. I mean, it's dimensional analysis, right? You take everything in there and you substitute it you substitute k for lambda k, et cetera. All the lambdas drop out. And so the equation of motion is unchanged. The evolution equations. And so if you had, the only other thing to pay attention to then is the initial, yeah. K is the wave number of the perturbation. So that's the perturbation wavelength. So just in the framework of evolving a single Fourier mode at a time, we need to scale that up too. Ah.
Those are two different lambdas, I assume.
Yes. Thank you for saying that. This is inconvenient. I remember being in a lecture by Eugene Parker when I was a graduate student, and he had introduced a third thing called W, and I asked, could we call this something different than W? And he said no. Okay. So the only other, so what's important? Of course, the equation of motion is important to what you what you get out at the end. So are initial conditions. And so if we coupled that with a scale invariant right, we have this k goes to lambda k, but if the power around wave number k is the same as the power around wave number lambda k, that doesn't matter for the initial conditions. I should have said that, you have to write the equations, the evolution equations, you're evolving dimensionless quantities. That's important to this, because the net result of these two things is that dimensionless observables don't change. I mean, of course, we're taking this to this, so we're scaling up the Hubble rate. So the expansion rate's going to change, right? That's a dimensionful quantity. But delta t over t, delta rho over rho, these things aren't changing. So we discovered this. It was we discovered this. This was my graduate student, Fei Ge, my collaborator at the University of New Mexico, Francis Jan Racine, and me, just 3 years ago. And that's the origin of the name, fat scaling for free fall. Oh, shoot, there's one other thing I need to explain before I get to the name. But the name is free fall amplitude and Thompson scaling. Why amplitude? Well, you can drop this assumption of scale invariant initial conditions. And if you have a power law, then all you have to do is adjust the amplitude of the power spectrum sum to make up for this change. If you have some departure from complete scale invariance, so if we have some power law for the initial power spectrum, then all we need to do to complete this scaling transformation and generalize this to a power law, initial conditions, when ns is different from 1, is to complete this with as goes to as over lambda to the ns minus 1. OK, so we can forget the k to lambda k. That's not a, anyway, that's just how we label different perturbation modes. This scaling with this, that's fat scaling. For free fall, amplitude and Thompson rate scaling, Or as I realized recently, Fay, Francis Jan, and this other guy scaling. So what good is it? Well, it actually pointed us towards constructing a model that can evade these constraints on light relics and get a much higher value of the Hubble constant, even higher than is desired by the most precise direct measurement of the expansion rate. Okay, but there's a serious, the model is, depending on how you look at it, pretty baroque, okay? And I don't think that the particular model that we came up with is what nature is doing. I'd be really happy if it were. It doesn't look like it. But so I think that the real takeaway for us from the scaling relationship is that it allowed us to understand the structure of the theory better in its relationship to observables. And I think that will last, although our attempt to use it to solve the Hubble constant problem, I don't know, maybe there'll be some modification to it that will answer the questions that model brings up. We'll see. Yeah?
Should I think about the lambda as a function of time or fixed?
That's fixed. Thank you for asking. That's just yeah. Everything else here is time varying, but lambda itself is constant. That scaling parameter. So there's a big barrier to implementation, and that is that we actually know the density of photons today, and we know the value of G, big G. So, so we can't scale up the photon density today, and as you just pointed out, lambda's constant here, right? If we can't scale it up today, we can't scale it up anywhere. I mean, this says this is measured really well, and so if we look at that transformation, how lambda is defined, we find lambda is 1 to very high precision. Okay, so we can't do it directly, but we can actually create a transformation that mimics this, and we can do that by adding in dark photons. So have some relativistic particles. They could even, obey the same. They could even be gauge particles of the same kind of symmetry as in electromagnetism. Just make sure they don't interact with the PHI-RAS satellite, because PHI-RAS does not see these things. And it's important that that these things source gravitational potentials exactly like the light photons do. So right in this plasma, the energy density of the photons is significant. It's a significant source of gravitational potentials. We need to have these dark photons sourcing gravitational potentials in the same way. Basically, where there's an overdensity of light photons, there should be an overdensity of dark photons. And this requires just like the light photons do, from being in a fluid to being free streaming. Because it's important that we do more than just increase the energy density in photon-like things. They have to source gravitational potentials in the same way. But we can easily do this. We just introduce dark atoms. So we've got dark photons, dark atoms. Remember, we also need additional light relics. So we need to scale up the neutrino, or something like neutrino density as well. And so if you like, we also need dark neutrinos, if I can call them that. And this sounds like a lot to ask for, right? It's a whole bunch of new ingredients to add. But if you think of it as just one dark copy of the standard model, then it's not, is it too much to ask for? And we didn't even invent this, right? For other reasons related to solving the hierarchy problem, which I couldn't tell you about, others have, and this is called a mirror world dark sector. Thank you.
I have a question. So if we're introducing dark atoms, how do we ensure that they have the same ionization energy as regular atoms?
Great question. Right. So I said that I wanted this because we want this fluid to free streaming transition to happen. And the question is, how do we make sure that this happens at the right time? And actually, soon after we wrote so I'll give two answers to that. One, I don't know. I'll give three. That's the first one. Two, actually somebody else wrote a paper. I think the first author was Gordon. I'm going to get the name last. There's an N in there too somewhere. Thank you. Anyway, great guy. Sorry to get his trouble with his name. And where anyway, they argued that actually that they could solve that question, right? And where you might naturally expect this in their model. And the third thing is that we're actually not critically dependent on this. And we've also explored in this model space what happens if we depart from this, really just pinning down that recombination happening at the same time in the light and dark sectors. And that led us to a potential solution of something called the sigma 8 tension. Yeah.
You probably said it, but maybe you can just repeat it again. I'm not sure if I understand what you mean by like from the fluid to free streaming.
Oh, so the photons go from being basically behaving like the collection of photons behaving like a fluid, meaning that any individual particle is rapidly, before it travels any distance, is rapidly scattering off of something. And so you can characterize this whole system of particles with a fluid description where you just have to specify a density and velocity. And then once the free electrons are all hidden in the atoms, then the photons are just traveling freely. And that has a difference in how they're sourcing gravitational potentials. And that's the important, so we need these dark photons to be sourcing gravitational potentials in at least a similar way, right? You need it to do exactly if we're going to have exactly this scaling, but we don't need exactly this scaling. But I'm not done. We don't have this yet. So we're able to, effectively mimic this thing. And then this, one way of doing that, I was really glad for this question earlier because it allowed me to introduce helium. And so if we lower the helium abundance, then we can scale up the Thomson scattering rate. So that's how we do it. It works. So you can implement this, and as you'd expect, it works. I mentioned that we're not scaling up atomic reaction rates, and that actually you can see the effect of that in our constraints, but it's a really mild thing. You can get very high values of the Hubble constant. But we run into a couple problems, one of which is that really to get all the way up to the Hubble constant from the direct measurements, we need a value of helium that is less than people have observed in the universe. And anyway, I have different takes on how much we should respect those measurements. But there seems to be a problem that we get less helium than is observed in the universe. That less primordial helium than is inferred from observations. And then also, right? Part of this, we've scaled up the density in light relics. You may have heard that BBN puts constraints on light relics. And so at least out of the box, and this is already kind of Baroque, we're getting the wrong, we have problems with light element abundances, right? And even internal inconsistency. What happens from standard BBN if you increase the density of light relics? You get more helium, not less. So we have this internal inconsistency. So those are the puzzles that I referred to, which is saying why I don't think this is what nature is doing, but it was a fun adventure, and maybe it'll lead to something someday. Understanding the scaling transformation is helpful for us understanding how, certainly for how light relics get constrained in more general model spaces, having that analytic understanding. And I think I'm out of time, so I will stop there. Thank you.
I have a follow-up question.
Yeah, we have time for one question. Go ahead.
So if you have these dark atoms, then also, and they have the same ionization energy as our matter, how do you stop them from collapsing more than they do from a halo into something more compact, just like regular matter from like black body radiation?
Yeah, right. So that's right. So you have these dark atoms, and